Welcome to Lecture 12. In this lecture, we will give our last examples on dynamic programming. We'll first talk about the problem on matrix chain multiplication, and after that, we will introduce a problem called optimal binary search tree. So let's start. First of all, let us review what is meant by matrix multiplication. So we have two matrices A and B. The dimension of A is RA times CA, where RA is the number of rows in A and CA is the number of columns in A. And similarly, the dimension of B is denoted by RB times CB. Here, we assume that CA, the number of columns in A, is equal to RB, the number of rows in B. Now, if this happens, then we can multiply the two matrices A, B to get AB. And this resulting matrix will have dimension RA times CB. And computing each entry of AB takes CA operations, so the number of operations to get AB will be equal to so many entries in the resulting matrix, and then each entry takes this many operations. So the number of operations to do this multiplication can be done in order of RA, CA, CB time. So here is a small example. So here A is a 2 by 3 matrix and B is a 3 by 2 matrix. So the resulting matrix will be a 2 by 2 matrix. So in a 2 by 2 matrix, we have 4 entries. And then for each entry, let's say the leftmost corner on here, upper leftmost corner here. Then to compute this value, what we need to do here is we are going to take the first row and the first column of A and B respectively and get the so-called inner product. So we have 2 times 1 plus 5 times minus 1 plus 1 times 2. So we get the value of this one and then we obtain the value here. So in order to get this value, so it is equal to or proportional to the number of entries in A's column or the number of entries in B's row. So it takes CA time. Okay, now let us extend the so-called matrix multiplication to get the product of three matrices, A, B, C. Let's say the dimension of A is 100 times 1, dimension of B is 1 times 100, and dimension of C is 100 times 1. Now, the meaning of getting A times B times C, we can do so by getting first what is the result of AB. Once we have the result of AB, this will be a matrix, and then we can further multiply this with C. So we get ABC equals to, we first get the result of AB, and then multiply with C. Now doing so, the number of operations using our previous analysis is proportional to, the first operation is to get AB. To get AB, it is 100 times 1 times 100 operations. Now once we have the result of AB, then we will have a 100 by 100 matrix. And in that case, to get the result of AB multiplied with C, then we will need another 100 times 100 times 1 operations. So in total, it is 20,000 operations. But interestingly, for matrix multiplication, it is actually an associative operation. So if you want to get A times B times C, so one other way to do so is we can first get the result of BC and then multiply A with this resulting matrix. So we can do so. A times B times C is, we can first get the result of BC, and after that, we multiply A on the left-hand side. We get this one. Now to get the result of BC, so let's take a look of B and C here. So using our previous analysis, the number of operations is proportional to 1 times 100 times 1. So 1 times 100 times 1. And after that, this BC will be a 1 by 1 matrix. So to get the result of A multiplied by this 1 by 1 matrix, then the number of operations will be 100 times 1 times 1. So in the end, after doing this summation, we get 200 as the value. Now the previous calculation takes 20,000 operations, while this new way of doing the multiplication only requires 200. And both of them are computing the same thing. So we see that by rearranging the order of multiplication, we could get the same correct result, but here it is much faster. Okay, now this is our problem today. So for our problem, we have an input of n matrices. Let's call them A1, A2, A3 up to AN. And we denote the dimension of AJ as RJ times CJ. And here we assume that the corresponding dimensions of these matrices, they will match each other. So the number of columns in A1 is the same as the number of rows in A2. The number of columns in A2 will be the same as the number of rows in A3, and so on and so forth. So they match each other so that we can multiply them together. And now we want to compute the product of this one, A1 times A2 times A3 up to AN. So we want to get this product, get the result, using the minimum number of operations. So what should we do? Okay, what is the order of the multiplication that allows us to do the best? So we could think backward. This is the usual way of solving a problem with dynamic programming. So to think backward, we will think, okay, what information we wish to know in order to determine the last matrix multiplication operation. Now for the last multiplication operation, it may do either, so for the last operation, it is something like we may already obtain the product of A1 up to AK, and then AK plus 1 up to AN. So we get this matrix, the product of this one, and the product of this one, and the last operation, just multiply these two together. But then this may occur for any k. So we do not know at this point what is the best sequence of multiplication operations. But for a certain best sequence, there will be the last multiplication operation. And for the last multiplication operation, it must be happening for some k, where we are multiplying the product of A1 up to AK with the product of AK plus 1 up to AN. Now to help us make the decision, so it will be great if somehow we know what is the minimum number of operations of getting this, and what is the minimum number of operations of getting this. So in the end, after applying the last multiplication, we know the number of operations of getting the whole multiplication. So based on the previous idea, so let us design what information we hope to store. So here we used best ij to denote the minimum number of operations to multiply ai plus 1 up to aj. So we want to multiply a subsequence of matrices here, okay, but they are contiguous, ai plus 1 up to aj. And then based on this meaning, so the best of ii is equal to 0 because we don't need to do any multiplication. This is just a single matrix, so no multiplication is needed. But for general best ij, the best one is, we will first find out what is the, so there must be a certain last multiplication. At some point, we are going to multiply ai up to ak for certain k, and then ak plus 1 up to aj for that one. So in that case, the number of operations will be best of ik plus best of k plus 1j. And after that, we get the two products. So the product of ai up to ak and the product of ak plus 1 up to aj. And in the end, we perform the last operation on the two resulting matrices. So the operations will be ri times ck times cj. So you can check this easily. We don't know which k will give us the best result. So we would simply consider all the possible k that we could have. So k could be equal to I plus 1 up to j minus 1. Yeah, because if it is j, then it is already outside the bound. So we consider all the possible choice of k and compute this value and choose which one gives us the best way. So we take the minimum of them. So by doing so, then we can compute best of ij for any I and any j recursively. So in particular, there are order n square best entries that we need to handle. So because I can range from 1 to n, j can range from 1 to n. So we get best of 1, 1, 1, 2, 1, 3, blah, 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 up to best of n. So we have order n square entries of best we want to compute. And to compute a particular value of best ij, the maximum time will be this general case, because we need to consider different variations. There are at most n variations of k that we need to take care of, but then for a particular k, this takes constant time to retrieve because it is already a computed value, constant time to retrieve this one, and constant time to get this product, so constant time to get a particular value of k for consideration. So that means that to compute best of ij, the time that we need is at most order n, because there are order n choice of k. Each k, it takes constant time. So in summary, n square entries, order n time for computing a certain entry, so the total time is order n cubed. And finally, the minimum number of operations that we want to find out is obtained at best of 1n, because it is meaning the minimum number of operations to get the product of a1, a2 up to an. Now, once we have this best table constructed, we can easily use backtracking, the standard backtracking, to obtain the optimal sequence of multiplication. So this is how one can find out the best order of multiplication in the matrix chain multiplication problem.